So today we will give actually an overview of the data products from DSC in DR3. And so DSC refers to the discrete source classifier. And we will present the architecture, the limitations, the DR3 results, and few perspectives for the upcoming data release. I will take over the first part of the presentation, and Corinne will actually take over for the second part. So our presentation is structured as follows. So we'll give a brief overview of the extragalactic results in GDR3, so Gaia Data Release 3. After, I will switch over to describe the discrete source classifier, the architecture, the limitation, and the main configuration of the module. The second part will focus on the extragalactic candidate tables and our perspectives and conclusions in the last part. So for the extragalactic results in GDR3, we have main results, and among the results provided are the classification of Gaia objects. So the classification can exploit actually the BPRP spectrum, as we also call the I do see a question on the chat, so please interrupt me if this is directly linked to my presentation. So the BPRP spectrum and also the astrometry and photometry. So in this slide, you would see that the different modules contributing to the extragalactic results in GDR3 are given in the in parentheses. So for instance, DSC is based on the XP spectra, photometry and astrometry. The variability is exploiting the temporal evolution that can be actually seen in the photometric light curves, and so on. So the classification is actually identifying types of objects, quasars, galaxies, stars, and also maybe having the trying to identify in which evolutionary stage, which is the part of the Vari module here. So among the extragalactic results in GDR3, we also have some input lists from the fit of brightness profile for extended objects, and also having some astrometry information from the similar to the CRF3. Redshift estimates are provided for the extragalactic results, either for quasars and galaxies. So the two modules, QZOC and UGC, are part of this webinar series and will be detailed in these webinars. So across the presentation, you would notice links that are provided. So the PDF of this presentation will be provided, so we can have direct access to the documentation and the various papers referring to this talk. Now I will switch over to presenting DSC. So DSC is a probabilistic classifier that is based on a combination of multiple modules. So first we have spec mode, ALOS mode, and finally we combine the results into com mode. Now I will go into details. So spec mode is actually exploiting the BPRP spectra. So these spectra were presented in the first webinar by Renee Andrea, and we will directly go into how we use the BPRP spectra. So the definition, you can actually find them in the Gaia documentation. So spec mode is actually exploiting the feature in the BPRP spectra to try to identify objects into 5 classes: galaxies, quasars, anonymous, white dwarf, and binary stars. So the second module, called ALOS mode, is a Gaussian mixture module that is trying to actually exploit a list of discretized features as the parallax, the proper motion, the galactic latitude, the relative variability, the brightness, the UV, the color. So all these features, for instance, are discretized and exploited by the second module to try to classify into 3 classes: the quasars, galaxies, and anonymous. An important mention here is that the anonymous class refers broadly to everything that contains also a point source star, for instance. So the last module, com mode, is actually trying to combine both predictions from the different modules into a singular one. Yes. So in DR3, we had this configuration of having 5 classes predicted by spec mode, 3 classes predicted by ALOS mode, and com mode is given the prediction over the 5 classes. And I should mention now that the prediction in DR3 for the white dwarfs and binary stars are considered not very satisfactory. So we would advise the user to mainly exploit the quasar, galaxy, and anonymous predictions over the entire DSC products. So, as we said, DSC is a probabilistic classifier, meaning that the output is probabilities per target class. We are given probabilities, so this gives flexibility to the user actually to define what is the best predicted class. And as in addition to the probabilities, we defined in DR3 two labels. One is the class label DSC, and the second one is class label DSC joint. So class label DSC is based on the outputs of comp mode, and comp mode is so for this label, we are setting actually the threshold to be higher than 0.5. So meaning if the probability for a quasar is higher than 0.5, then the label is actually set to quasar. That will be similar for galaxy, anonymous, and all of the classes for comp mode. If the probability does not respect this condition, we are setting the label to unclassified. So for the second label provided in DR3, which is class label DSC joint, this one is actually putting a threshold jointly on the outputs from spec mode and the outputs from ALOS mode. So this is an end. Both classifiers should actually give probabilities higher than 0.5. And this is how we set the labels, which actually allows us to remove a lot of contamination. So here we are presenting this, just one example for quasars. This applies for galaxies. We should note that the two labels, class label DSC and more importantly, class label DSC joints, are exploited to define pure set for the extragalactic tables. So in this slide, you would notice two links provided. So one is the description of the module, a thorough description of the DSC in DR3. And the second one is a link to the documentation with further details. Okay, so that was the presentation of the architecture. Now I will talk a little bit more about the training data. So the training data, if you notice that we have two types of inputs. One is the spectra for spec mode, and the second one is a list of features for the ALOS mode classifier. So for the ALOS mode, we are aiming to identify the quasars, galaxies, and stars. And in this presentation here is the distribution over all the features that were used in cycle 3. So you would see, for instance, in the first panel upper left is the Gmag, which is the brightness of the object. And you would notice that for the galaxies, they are mostly, the range is between, is peaking at about 20 in Gmag. So you would notice that in these kind of distributions that the three classes are lying differently in the feature space. So ALOS mode is exploiting this high D dimensional data to actually try to identify the aggregates of similar objects. So this is another representation. So I just showed the 1D representation, but ALOS mode is actually based on the 8-dimensional data that we are providing. So here actually a representation of 2D in the CMD, which is the color magnitude diagram on your left, and on your right is the color diagram of the three classes provided for ALOS mode. So again, we have a distinction between quasars, galaxies, and stars that do lie differently. So if we add up the different features, we are able actually to distinguish. You should note that the distributions are not centralized, but this is quite normal because the sources are actually extracted from the Gaia data. So we would expect a little scatter around the main distributions. So that was the first part of the input data, which was the set of features. The second part is the XP spectra, so the BP and RP spectra. For the spectra in this slide, I'm showing actually the corresponding SDSS spectrum. So that will actually give you an indication about the spectral lines and spectral features that are present in higher resolution spectra, but also can be seen in the BPRP spectra. So in your upper right, you would see two examples of quasars at different redshift. One is about at redshift 3.2 and the second one at redshift 2.5. At these redshifts and the wavelength range of the observation, we would so we are in the optical. We actually can easily notice the Lyman alpha lines and also some carbon 4 and carbon 3 emission lines in the quasar. In addition to just right before, so the Lyman alpha lines is the most dominant line you are actually looking at. So for instance, it is here at 550 nanometer and after 400 nanometer at these specific redshifts. And right before is the start of the Lyman alpha forest. So as soon as we are moving across higher redshifts, these features are actually moving to higher wavelengths. And you could see actually the evolution also in the BPRP spectra. So for the galaxies are, so two examples. So this is not actually representative of the entire training set we're providing. So for the galaxies, I'm showing two examples, one of the starburst galaxies and one just of the what SDSS classified as star forming. So for the starburst, they refer to galaxies with higher star formation rate. So you would notice that in the high emission line for H alpha at about 680 nanometer, and which is also can be seen in the other galaxy of the star forming one. So in SDSS, the emission lines are very clear, but you could also see this type of feature in the BPRP spectrum. So coming last to our to the star class, for instance, in the lower left part of this slide, you would actually see different behavior, and this actually links to different stellar types. So the main dominant features in the spectra are broad absorption lines, and also we could have a slope in the continuum due maybe to dust. So these are the input data for the spec mode module. I would have to mention that the training data for DSC in cycle 3 in the data release 3 was based for quasars and galaxies from spectroscopically confirmed objects from SDSS that we actually cross-match with Gaia data. And the input of our classifier is the Gaia data. So the sources from the star class is a random selection across all the Gaia parameter space and across all the sky for a list of objects that are not included in the quasar and galaxy sources. So here I finished presenting the training data and the architecture, and I will move over to the class prior. So DSC is probabilistic classifier. So the output is, so the main output is a list of probabilities. These probabilities should be adapted within a Bayesian framework to actually depict the true distribution of sources across the sky. And for that, we apply a prior. So this prior, as you see here, is mentioned in the first, in our papers. And this is what we call as a global prior. So the global prior is extracted from Baylor-Jones 2019 paper and also from observations in different surveys. So these fractions are actually used to correct the outputs of the classifiers into posterior classifiers that include this class prior. There is an important note here is that after we obtain the posterior probabilities, we are computing the performances of the models. So these performances are quantified usually by metrics like as the completeness and the purity and so on from a confusion matrix. So the confusion matrix is a direct comparison of our validation data set and our prediction data set. So when actually we compute the metrics, we have to take into account that these results should actually depict, once again, a correction on our validation data set. We apply a second correction, and this is what we actually mention in this note here. If we are given the direct results from the true posteriors, the results of the purity and completeness are always 99 or 94% correct results. So when applying this correction here, we are actually trying to give you what is the expected results that will be observed across the entire Gaia catalog. And this is this brings me to this chapter here, which is the performance in Gaia DR3. We are showing here the spec mode, ALOS mode, com mode, and the last class label DSC joint results. And the completeness and purity mentioned in this slide are actually after correcting with the validation set and the class prior. So the quasars, galaxies, and stars, you would see that the completeness is very high for galaxies and stars, and the purity is low. So there is always a compromise between the completeness and the purity. So the completeness, I have to define it as the ability of the system to recover the true labels. The purity is how much we inject false detections. So there is always this compromise in maybe we should reach high completeness and the purity having a lot of false detections is not affecting a lot the results. Moving to ALOS mode, there is actually dealing with different types of inputs, which are the features. You would notice that the completeness for quasars is increasing a lot, as well as for galaxies. So the purity is almost comparable to the results of spec mode. What is happening is that the purity of quasars and galaxies is very modest because any contamination from the star class is highly enhanced because of the class prior of the stars that are expected to be the majority of sources observed across the sky. For com mode, the completeness and purity is even corrected. We would see then that the completeness of all three classes is over 90%, which is a good result because we are able to actually recover the true labels. The purity is still about the same performances, but once again, it is due to contaminants from the star class and the effects of having a lot of stars actually that we are observing. For the spec mode and ALOS mode results, so here we are showing only the quasars and galaxies because this is the definition of the class label DSC joint, meaning how well we are able to recover these two classes when applying the cuts as 0.5 in probabilities from both spec mode and ALOS mode. So I should mention once again that the first two modules, we are defining these results from the maximum probability. And for the class label DSC joint, because we are actually setting a threshold of higher than 0.5, we're actually able to correct for the purity, meaning that we are able to reject a lot of contaminants. So you would also notice that the completeness is quite close to the results of spec mode for the quasars and galaxies in this point here. So the results presented in GDR3 are actually depicting the full results across the sky, which should actually take into account the brightness and also the galactic latitude of sources, meaning that we have actually to provide better estimates to the performances as function of brightness and galactic latitude. So if we avoid actually the galactic plane, here we are showing actually the results for the quasars and galaxies outside. For these updated results, the class prior is adapted because we are actually correcting the class prior for the region outside the galactic plane. And applying this modification, we are actually able to increase once more the purity in the class label DSC joint. So these were the main results in GDR3, and all of our results are accessible through the archive. So the link is provided here, and you also have direct indication on where to find the different results from DSC. So common mode probabilities are provided in the main table, and if you are interested in having access to spec mode probabilities, ALOS mode probabilities, and common mode probabilities as well, they are also provided in the astrophysical parameter table. The extragalactic tables, the galaxy candidates and quasar candidates, are also part of the DR3, and you can actually have direct access to common mode probabilities and the class label that we just described. And if you put thresholds as defined by Baylor-Jones 2022 papers, you would be able actually to have a stricter and purer set of galaxy candidates and quasar candidates. So in this part, I would leave Corinne to present the second half.
Okay, thanks, Sarah. Okay, so you can see my screen, I hope. So I'll just carry on where.
Yes.
Thanks, where Sarah left off. So the important thing to realize, of course, is that DSC is not the only classifier identifying extragalactic objects in Gaia DR3. There are a number of other packages from other coordination units using different data, which Sarah mentioned at the beginning. And so one of the papers that we wrote for DR3 tries to summarize the main results from these papers. And so one of the figures from the paper produced by David Tassier is shown here, which you'll probably want to look at separately in the paper to fully digest it. But this is just giving an idea of the content and origin of the so-called extragalactic candidate tables. And I emphasize the word candidate here because, of course, we don't claim very high purity for various reasons I'll mention. And so you can see the different classifiers. For example, on the left for the quasar candidates, we've collected a set of something of the order 6.6 million candidates, although a purity of only around 50%. And you can see which of the different modules are contributing to this. And you can see quite a large amount is coming from DSC because of its focus on completeness rather than purity in DR3. But there are a number of additional candidates being proposed by other classification algorithms. So there's the surface brightness classification coming from CU4, there's the variability classification coming from CU7, and the set of sources that was also originally selected for the Gaia Celestial Reference Frame 3, which was published as part of Gaia DR3 as well. On the right, you can see the similar thing for the galaxy candidates. We have a slightly higher purity and a slightly smaller set. I should say that not all of these are being identified by the Gaia data. Some of them are relying on input lists. For example, the list from CU4 was an input list, which was then analyzed and refined in the context of the Gaia DR3 work. So one important thing to realize about the extragalactic candidate tables, which you can find in the archive, is that there's no common definition actually of quasar or galaxy across the modules. And this is sort of inevitable because each one is using different data. And so that really prevents a very consistent definition. So you should be aware of this when you're using the definitions are given in the various processing papers. Likewise, as I mentioned, the purity and the completeness of the different modules varies, and it will vary therefore amongst the subsets selected. So as I said, the input lists and the variability driven classification, or the variability provided classification, is concentrating on trying to get higher purity, whereas with the DSC we focused on trying to get more completeness. But you can get a higher purity subset using further selections, which I'll mention in a minute. Obviously, this reducing the completeness necessarily. And when analyzing the results, you should keep one thing important in mind, namely that if you had a constant relative contamination of a certain percent, then of course the absolute contamination that you see, for example, in sky maps will of course just follow the source density, where you have a lot of sources, you have the same fraction of contamination, but therefore a lot more contaminants. And you'll see an example of that in a moment. An important thing to realize is what we did in DR3 was to only use Gaia data. So we intentionally provided results based only on the Gaia data. The training sets, of course, are using external data in the sense that they need to be labeled, so they've taken advantage of, say, typically SDSS, high-resolution spectroscopy to identify quasars and galaxies, but the individual sources themselves are classified only using Gaia data. And of course, in practice, there's a bit of a limitation for extragalactic objects, and we do expect higher purity if you have higher data. And I mentioned again, there's a link. This is a link to the collaboration paper, which has been published. It should appear it's on the ANA webpage, but it's not finalized, that special edition yet, but it's available, has been for about a year. So I mentioned you can get purer subsets of these extragalactic tables, and that's actually very easy to do with these two ADQL queries, which we put in the paper. It's just making a selection on various flags, and particularly in the case of DSC, it's using this so-called joint flag, which is where the probability from both the ALOS mod and the spec mod are larger than 0.5. And an analysis of this is provided in the paper and compared with the full set, but I can give you a very brief summary of that now. So you can see here sky distributions in in galactic coordinates, galactic center in the center, longitude increasing to the left. And you see on the left is the sky distribution on log scale of the quasar candidates, which we're only claiming to be about 50% pure. And you can see straight away, for example, that, as I mentioned, the contamination follows source density. And so you obviously expect to get a high degree of, a high density of incorrectly classified sources in high density regions of the sky. And you see obviously here the LMC and the SMC and parts of the galactic center, Sagittarius, etc., are standing out here. The other feature you see, of course, also in the galaxy map on the right, is that the source density is limited, of course, in the galactic plane by the presence of extinction of dust in the galaxy. So we're as expected, finding fewer extragalactic candidates there. You can also see, in particular, on the galaxy candidates on the right, some imprint of the scanning law from Gaia. This is because this happens preferentially with the galaxies rather than the quasars, because galaxies are partially extended objects, and therefore their detection and characterization with Gaia is much more affected by the scanning law, simply because Gaia is, of course, then scanning these parts of the sky at different angles. And for an extended source, it means that the source, the point source, the equivalent point source, which Gaia is detecting may differ from scan to scan. And so you're getting an effective variability in the source and variable detection for extended objects. So this is for the full set. If we go now to the purer subset, which we can identify with the query I just mentioned, you can see a radical difference. So let me just go between these briefly. This is the full set, the purer subset, which is, we think, around about 95% pure. And you can see that when we do this, the cost, of course, is a lower density of objects. But in particular, we're losing the galactic plane because this is where a lot of the numerical contamination is actually taking place. And you see also, particularly for the galaxies, actually, that the LMC and SMC are much lower density because the purity criterion is really eliminating a lot of confusing sources there. We can also look at the color magnitude diagrams of color diagrams, so color magnitude diagram on the left, color diagram on the right. Again, now for the full set of quasars in blue and galaxies in orange, and you can see a fairly clear separation here. Now you might think then, okay, this must make classification very easy, but of course you have to remember that the stars are not shown here. They outnumber both of these classes of objects by a factor of 1,000, and when you impose their density on top of this, which you can see plots out in the paper, then actually classification using only the colors becomes very hard. And in fact, even with the other features, still remains quite challenging, just given the huge number, and the huge superiority of the number of stars, which just swamps the classification scheme. But again, when we go to from the full set to the purer set, you can see this clearing up a bit in the sense that you see tighter distributions in both plots. We also lose, you can see on the left, some of the very faintest objects, particularly on the galaxies there, because of course they have low signal to noise and therefore low confidence classifications. Okay, so we'll wrap up now. I'll just hand back to Sarah for the last couple of slides on the improvements we plan for DR4 and just to give a summary. So over to you, Sarah.
Yes, so here we are listing actually a few points on the planned improvement for the next data release. So among the list of improvements, we do have a calibration of the posterior class probabilities. As you can directly have access in the DR3, the class probabilities provided by DSC can be a little bit extreme, meaning that we are a little bit over the 99%. So we are working on the calibration of the posterior class probabilities. A few points mentioned here about the algorithms, the hyperparameter optimization. So this is also a point that we are exploring right now. Another point is the prior as a function of brightness and galactic latitude. So we have a published paper on the method, which is on ANA and available in this just in here from PhD students in collaboration with Corinne and I. And the prior would be adapted. And from that, we have also the evaluation of the performances as function of brightness and galactic latitude, among other features from the sources. The last point is rejection of contaminants in the training set, meaning that we have actually to evaluate the performances of the model if the training data is highly controlled. So these are the list of planned improvements, and maybe now we can switch to our conclusion slides. So as mentioned through this presentation, DSC classifies sources into three main classes: star, quasars, and galaxies, using different types of input data as the XP spectra, astrometry, and photometry. And the extragalactic classes are defined by the SDSS, the spectroscopically SDSS sample. We are applying prior adjusted probabilities, and we give purity and completeness as depicting the real distribution across the sky. So meaning that the purity estimates takes into account the rareness of the extragalactic sources. So the main goal of DSC in DR3 was focused on the completeness, and we are working now into improving actually the purity, so meaning that rejecting the contaminants. The Gaia DR3 extragalactic tables come in from several modules as described by Corinne, not just DSC. You have different class probabilities, so you could actually select the pure set of candidates from the quasar table and the galaxy table by setting the thresholds on the class label joined from DSC, for instance. So you have 1.9 million quasar candidates and 2.9 million galaxy candidates. And also just to mention a last number, which is that DSC classified in DR3 1.5 million sources, billion sources. And I think we can finish on this note.